today's topic is again at the intersection of randomization and approximation. I might even also show you another example of parameterization in there, but we're going to focus mostly on counting problems. So at this point, most of the problems we've seen in this course have been decision problems. You just wanted to answer yes or no. We also talked about some approximation algorithms where you wanted to minimize or maximize the cost. But now let's say I have a decision problem, and let's say that my decision problem is in NP. And I just want to see how many solutions it has. Or if you recall the definition of NP, so what did we say when we were defining the class NP? We said that a language L is in NP if it can be verified that a particular string is in a language given a particular certificate in polynomial time. Okay, so L is in NP if and only if there is an algorithm, and this algorithm had to be polynomial time, such that what conditions did we want to have? Well, we wanted to say that the first condition was that if x is in this language L, then there exists a y such that a of xy returns 1. So this y was a certificate or a proof that x is in our language, right? And also we said that the length of this y has to be bounded also by polynomial limits. I'm going to get too lazy to write that, but just remember that part. And we said that this should be if and only if. So if x is not in L, then there is no certificate. If x is in L, then there is at least one certificate. Right? Okay. Now, and of course, since y's length is polynomial in x, and since this algorithm A runs in polynomial time, so the entire runtime here is also polynomial in x. Now, suppose that I go one step further and I ask you how many certificates are there for a particular x. So instead of just giving you some input x and asking you whether x is in this language L, I ask you how many certificates does x have. So what are some real world examples of this? So suppose that I give you, let's say, a SAT instance or a 3-SAT instance or anything like that. And I ask you what is the number of different valuations that I can give to my Boolean variables so that this particular formula is satisfied. So in a SAT instance, I'm asking for the number of satisfying valuations. Okay. Maybe I can give you a graph as the input, and then I can ask for the number of a bunch of different things. So maybe I give you a graph, and I ask you what is the number of maximal matches? Or what is the number of perfect matches? Or maybe I ask you what is the number of maximal independent sets? Anything that exists in the graph. Another example that, if we have time, I will get to it in the next session, is what is the number of spanning trees in this graph? Okay. So some of these problems are actually easy to solve and some are not. So for example, if I give you a graph and I ask you what is the number of spanning trees, there is actually a polynomial time algorithm for that. Again, if we have time, I will go into it. Otherwise, I will just give you some link to this app. But here's the thing. If I give you a SAT instance and I ask you what is the number of satisfying valuations, that's at least as hard as solving the SAT instance itself, right? Because if your answer is 0, that means that the formula is unsatisfiable. If the answer is 1 or anything more than 1, it means that the formula is satisfiable. So if I ask you how many satisfying valuations there are, this is strictly harder than asking you to solve the SAT instance itself. So it's at least NP hard, we know that. And the same thing happens in graphs. So actually, if I want to give you an example again, let's say I want the number of maximum matchings or the number of perfect matchings in a bipartite graph. Okay? So you can see that intuitively it seems like the counting problem is going to be harder than the decision problem. So if I just give you a bipartite graph, so let's say I have 2 parts in my graph. I have L here and I have R here. And there are a bunch of edges going from L. Okay. And let's say I ask you, does this graph have a perfect matching? And a perfect matching is a matching that contains all of the vertices, right? So this is something that you should have seen in maybe combinatorics courses or discrete mathematics courses before in your undergraduate studies. There is a theorem called Hall's marriage theorem. And the idea is that if any subset of vertices on the left have at least as many neighbors on the right as the number of members in that subset, then it's possible. Otherwise, it's not possible, right? So deciding whether I have a perfect matching is kind of easy using Hall's marriage theorem. And actually, there is a greedy algorithm for it, right? So you just assign randomly, and then you try to find the matching that is a little bit better, and so on. You can also solve it with network flow algorithms. So just imagine that I add some source vertex here, and I add a sink vertex here, and then I connect the source to every one of the vertices here with capacity 1, and I connect all the vertices here to the sink also with capacity 1, and I ask what is the network flow from the source to the sink. And if the flow is equal to the size of L, then I know that I have a perfect match. Otherwise, okay. But now, if I ask you what is the number of perfect matchings, this is suddenly a much harder problem. Right? And we will get back to this problem. But before going forward, let's consider again this example. Let's say I give you a SAT instance, and let's say that it has n Boolean variables in it. So what is the number of satisfying valuations? I want to ask that, but what is an upper bound on it? Well, in the case where I have the most number of satisfying valuations, I just have something that is true and everything satisfies it. Right, so I will have 2 to the power of n satisfying valuations. So if I just ask you how many there are, you can write this number, and it's a number between 0 and 2 to the power of n. So you can write it with an output size of O(n). You need n bits in your output, maybe n plus 1 bits in your output, right? But if I actually ask you what are all the valuations that satisfy here, so if I ask you to list all the Y's here, all the certificates, then that can definitely not be done in polynomial time, right? And because I will need 2 to the power of n times n just as my output size. Now, it can't even be done in polynomial time if I want some approximation, or if I even allow randomization, because again, my output size is just too large. But if I just want the number, then I might be able to use some combination of approximation, randomization, and parameterization and get the number, right? So I want you to see that there are these three really different variants of the problem. One variant is just asking whether there is a certificate Y or not. That's the decision variant. Then there is the counting variant, which asks you how many certificates do we have. And then there is what we call the enumeration variant, which tells you to output all the certificates. And these are not really the same problems. So we're going to focus on the counted variant. Okay. So I'm going to use this definition and this particular problem. I will get back to the other problems later. So let's say at first we want to consider the most general case of the problem. So I'm giving you some algorithm A that satisfies these properties. So instead of actually giving you the problem, I'm giving you this algorithm that verifies whether Y is a valid certificate for X. Okay? And then I ask you to solve the counting problem. So your input is this X and this algorithm, and you can run this algorithm, right? And I just ask you how many different Y's are there. And let's say that I fix a particular length for Y as well. Because anyway, the length of Y has to be bounded by a polynomial in X, so I can just assume that the length of Y was also given to me in the input. So my inputs are these. I have the algorithm A, which has all these properties. I have some X, and let's say that X has length n. So I had n different bits in my input. And I also give you some number m. And this m is supposed to be bounded by a polynomial in n. And then I ask you how many different Y's are there such that the length of Y is m and A of xy is okay. Now, how can you answer this? Well, we have a kind of a trivial exponential time algorithm, right? So I can just try every possible Y. So I know that the length of Y has to be m. I just try 2 to the power of m different cases for Y. And for each one of them, I just run A of x and Y. I know that A runs in polynomial time. So my total runtime would be 2 to the power of m times some polynomial. And I just count how many of these Y's I can find. Okay. And to be honest, I know that I can't do better than this probably, because this A might be the algorithm that verifies a solution to SAT, and I don't expect to have a polynomial time solution to SAT, of course. Right? Okay. But what if I can also use randomization, and what if I can also use approximation? Can I have maybe a randomized algorithm that gives me kind of an approximation of this? Okay, so first of all, I have to define what it is that I exactly want. So we've already defined the concepts of p-task and f-p-task when we were talking about randomized algorithms. When we were talking about approximation algorithms. But here, I want to do an approximation, but I want to do it using a randomized algorithm. So now my algorithm can have some probability of failure as well. Okay? So what am I exactly looking for? So this is what I'm looking for. I would like some algorithm. Let's call this algorithm B, since this one was called A. And what do I want it to do? Well, when I had the p-task or f-p-task, I always had some extra value epsilon, and I used that epsilon as my parameter, and it told me how close I have to be to the solution. So let's say I have that here too. So let's say that I have b epsilon, and so I want for any epsilon greater than 0, I want an algorithm called b epsilon. Okay? Now, b epsilon gets these things as its input. And what do I want b epsilon to do? Well, I want to say that the output of b epsilon, whatever answer it has, is within epsilon of the actual answer. So let's say, let's give it a name. So, I don't know, let's beta be the output of b epsilon when I give it x, right? So I'm giving this b epsilon my number x, and my input x, and I'm asking how many different y's exist such that a of xy is 1. I can also give it m, it doesn't really matter. If not, it can just try every m. Okay. So what do I want this beta to actually satisfy? Well, let me have another thing. Let's say that I call this one alpha. So the actual number of y's that can serve as a proof that x is in my language, I call that alpha. Okay? So I want this beta to be at most 1 plus epsilon times alpha. Right? Because I don't want it to be too far off. I want to have an approximation. But also, on the other hand, I don't want it to be too small, because now I can just output 0 all the time. So I want this to also be greater than or equal to 1 minus epsilon times alpha. Okay? So until this point, I'm just talking about basically an approximation scheme. There is no randomization here, and I haven't talked about the runtime of this algorithm. So how do we add randomization? Well, to add randomization, I can say that it can fail with some small probability. So I want my algorithm to always output something like this, hopefully. But if it fails, then it might give me a solution that doesn't satisfy this. And if that happens, then I want it to happen with a very small probability. So let's call that probability delta. So for every epsilon and every delta, I want an algorithm with parameters epsilon and delta such that when I run it, the probability that this happens, the probability that I succeed, is greater than or equal to 1 minus delta. Okay? So, again, this is exactly like what we've seen in p-TAS and f-p-TAS when we were talking about approximation schemes. The only difference is that I can have a randomized algorithm here, so I can also have some probability of failure. And so with probability at most delta, I would fail. With probability at least 1 minus delta, I would succeed. And when I succeed, I output something that is at most a factor of epsilon away from the actual answer. So here we don't really have an optimal answer, we just have one answer, which is the number of things that we do. So if I succeed, my output beta is between 1 minus epsilon times alpha and 1 plus epsilon times alpha. Okay, great. Now, what can I say about my runtime? So what kind of runtime do I like to have? So again, remember when we were talking about FP tasks, we said that we want our runtime to be polynomial in the size of the input, which was n, and also in 1 over epsilon. Okay? So here I say the runtime of v epsilon delta should be polynomial in n and 1 over epsilon. Okay, but now I have this extra bit delta as well. So what should I do with the delta? So I can say that it should also be polynomial in 1 over delta, right? But actually, the standard is to say that it's polynomial in the log of 1 over delta. Okay. Now, why is that? Because imagine that I have an algorithm which succeeds with some constant probability. So it fails with some constant probability as well. And if I want the probability of failure to become less than delta, I can just run my algorithm log of 1 over delta times. Right? So that's why I don't need 1 over delta here, I just need its log. So yeah, this is like a randomized, fully polynomial time approximation scheme. Okay? So this is what I want to achieve. Okay. But that's just the theory. Let's actually get into the problem and let's see what we can do for the problem of SAT or for any other problem that was. So here, the first solution that came to my mind was the trivial solution. It was just try every possible y. And we saw that that doesn't give us a really good run. So what else can I do? Since I can have a randomized algorithm, I can choose y randomly. Maybe I can choose y uniformly at random. So let's say that I just take a bunch of samples. So here's the thing. Let's say that this is the set of all possible strings of length n. And let's say that this is the set of strings that actually work, the set of y's that actually work. Okay? So let's give this some name. I don't know, let's call this one G, let's call this one H. Okay? So G is the set of y's, the set of proofs, certificates that actually work for this particular x, and H is the set of all possible strings of length. Okay? Now what can I do? I can just do sampling, right? So I can take some random member of H, and then I can just use my algorithm A to check if that random member was actually also in G. Okay? But the problem is how many samples do I need? So let's call the number of samples big N. So let's say this is my number of samples. I'll get back to how we can choose big N. But for now, let's say that I have some big N. So what do I do exactly to find the size of G, to approximate the size of G? Of course, I just take N samples, and some of them will be in G, some of them will be outside of G. Right? And I just look at the ratio of the samples which were inside of G, and I imagine that that's probably the ratio of the size of G to the size of H. Okay? So let's say that S is the number of successful samples. And by successful, I mean that they were in G. They were actually a proof that X is in the language. Okay? So what this tells me is that intuitively, the ratio of the size of G to the size of H should be something like this. S over N. Sorry, I don't know this. Okay? So I intuitively think that the size of G should be this number times the size of H. And let's say this is my beta, this is my output. Okay? Whereas what is my alpha? What is my actual answer? Well, my actual answer is basically just the size of G over the size of H. Okay. This whole sampling algorithm, this is called Monte Carlo sampling. And you can actually use it for all sorts of different problems as well. So forget about what we're doing here. This is a much more general thing. So if I give you some general geometric shape, and I ask you to compute its area, and somehow you have a way of deciding whether a particular point is inside this shape or outside of it, you can just create some other shape, so maybe a rectangle that includes this, and then you can just take random points and see what proportion of your points are actually inside your shape G. And then you just take that proportion, and that gives you an estimate of the area of G. Okay. Great, so let's say I do this. Now, of course, alpha and beta are not necessarily the same. Beta is intuitively just an approximation of alpha. But I want to find this probability. I want to find the probability that the approximation that I get is actually close. So this is what I want. I want to know the probability that beta is between 1 minus epsilon alpha and 1 plus epsilon alpha. And I want to make sure that this probability is at least 1 minus delta. Okay? But what is it that I can actually control in this process? So this is my goal. But what kind of choice do I have? Well, really the only choice that I can have in this simple algorithm is to choose how many samples I want to take. So the question is, what is the minimum number of samples that I should take so that this inequality holds? So how many samples should I take until I make sure that my approximation, which was obtained like that, is tight enough? Okay. So let's do some analysis here. Okay. So let's define some variables, and I can just define these variables exactly as we did before. So let's say that I say y is the random variable of the number of successful samples. Okay. So y is basically going to be the size of this. Or actually, the notation simpler, let me just call it S. I used it as a set there, I'm using it as a number here, but don't worry, it's just the same thing. S is the number of successful samples. So I can write S as a sum of indicator variables. I can say that S is S1 plus S2, so on, Sn, big N, where every Si is 1 if the I sample succeeded, and it's 0 otherwise. Okay. So now I can talk about the expected value of S. And all the things that we used to do before. So we can talk about the expected value, we can talk about variance, and then we can apply Markov, Chebyshev, or Chernoff. And actually, I'm going to apply Chernoff. Okay. But what is the expected value of a particular SI? So, one SI is just the result of one of my samplings. So I'm choosing a point uniformly at random here, and then I'm just checking whether it's in G or not. So the probability that I succeed is just going to be the size of G over the size of H. Oh, sorry. Your alpha was just the size of G. Okay. Nice. So let's give this thing a name. Let's call this one maybe rho, because I'm too lazy to write size of G over size of H. So now what is the expected value of S? Well, these are n independent random variables, and I mean, for linearity of expectation, I don't even need the fact that they're independent. So the expectation of the sum is just the sum of expectations. So this is just rho times n. Okay. But what is rho times n? It's actually, in a sense, kind of like our optimal answer. So if I didn't have a distribution here, and if everything was exactly this amount, then I would get the optimal answer. Right? Because if each one of these was exactly equal to the size of G over the size of H, instead of just being equal to that in expectation, then I would always get the right final answer. But okay, here the only thing that I know is that I'm going to be right on average, in a sense. So the question that I have to answer is, given that this beta is right on average, it has an expected value that is the same as alpha, right? What is the probability that it's between these two different values? So let's see. Okay. In other words, let's just write this probability in a different way. So I want the probability. Okay, that's my probability of success. Let me write my probability of failure. My probability of failure is the probability that either beta is less than 1 minus epsilon alpha, or beta is strictly greater than 1 plus epsilon alpha. So it's the probability that beta minus alpha is greater than or equal to epsilon. Okay. Where have we seen this before? So when we were talking about Chernoff bounds, we had a situation like this, where we wanted to see what is the probability that a random variable deviates from its mean by more than some amount. Okay. But let's try to write it in terms of those things. So what is beta? Beta is S divided by N times H. So I want the probability that, okay, this beta was again S over N times H minus, what is alpha? alpha is just G. So I'm not going to write the sizes, I'm just going to write it like this. It's easier to understand. This is greater than or equal to epsilon times the size of G. I want to write this only based on S, right? Because when we wanted to apply a Chernoff bound, we should always have something that looks like this. It's a sum of independent random variables. So here, actually, maybe this is just making it more complicated. So I want to see what is the probability that this beta is off by a factor of epsilon, right? Do you agree that that's the same as the probability that S is off by a factor of epsilon? Because when I want to get beta from S, I'm just dividing and multiplying by some constants that were given to me in the input. Okay? So I can say that this is the same as the probability that S deviates from its expected value by more than epsilon times the expected value of S. So, what did we have in Chernoff bound for this? So if you remember, I gave you a general version of Chernoff bound, and then I gave you like a slightly weaker version that was actually easier to apply. And the slightly weaker version was this: the probability that some random variable x deviates from its expected value mu by more than some delta times mu was at most, well, I never remember these things, so I have to write it like this. So it was 2e to the power of minus delta squared divided by 3 times mu. Okay, so this was what we had from Chernoff bounds. Okay, what happens if I apply this here? So I know that this probability is at most, okay, I have 2e. What is my delta? My delta is actually epsilon. So minus epsilon squared over 3. And what is my mu? My mu is the expected value of S. So expected value of S was rho n times rho n. Okay. So this was my probability of failure, and now I have a bound on it. I know that the probability that my algorithm fails is at most this much. But I want this bound to be at most delta, remember? So delta was the maximum probability of failure that I could tolerate. So I just say what happens if this is exactly equal to delta, or if this is less than or equal to delta. So I should have 2e to the power of minus epsilon squared over 3 times rho n equals delta. And again, in this equation, the only thing that I can really control is n, right? Because, of course, epsilon and delta were just given to me. Epsilon was the approximation factor, delta was the probability of failure. I have no control over those. And what is rho? Well, rho was just this ratio of the number of valid answers to the total number of answers that I can try. And again, this is not under my control. This is part of the problem. So the only thing I can control is n. So what value should I choose for n so that this equality applies? Well, you can just take the log of both sides and then you can solve for n. Right? So if I take a log from both sides, so this thing comes out, again, take a natural log. And then here you will have log of delta. Let me see. I don't like to do too much calculation. So again, this is what I asked Wolfram Alpha to do for me. So I can just set n to be 3 times the natural log of 2 over delta divided by epsilon squared rho. Okay. And if I do this, then I am guaranteed that this problem works, that this solution works. So, in other words, there is a particular number of samples that I need to take before I can be sure that my sampling is actually giving me an approximation ratio of epsilon, of between 1 minus epsilon and 1 plus epsilon, with a high probability, with probability at least 1 minus delta. Okay. But is this good enough? So, again, everything that I said here can be applied to any problem. This wasn't just for SAT, it was for any problem that can be modeled like this, and then you can do Monte Carlo sampling. But what happens in the particular case of SAT? Okay, so now let's go back to here. Let's say I've given you a SAT instance, and you're just counting the number of satisfying valuations. So how big should this number n be? Okay. Again, delta and epsilon are parts of the input to us, and that's fine because if we take n samples, for every sample we are spending polynomial time to check the sample, and this part is polynomial in the log of 1 over delta, and this part is polynomial in 1 over epsilon, so these are all good. The only problem is with the rho. So what is rho? Rho is the ratio of actual answers to the total number of potential answers that we could try. So if I have a SAT, and let's say I have n variables in my SAT instance. Okay? What is this rho? In the worst case. The worst case is that my SAT instance can actually be satisfied, but only by a unique kind of valuation. There's only one valuation that satisfies my SAT instance. And then, so the size of this G would be 1, and the size of H would be 2 to the power of n. So my worst case is that my rho is 1 over 2 to the power of n. And if that happens, then how many samples do I need? Well, I get a 2 to the power of n factor here. Right? So basically, we didn't really achieve anything with all of this kind of work that we did here, because in the worst case, I'm still as bad as just trying every possible value of 1. Because the number of samples that I need is going to be huge. It's going to be exponential. Okay, but I want to, of course, improve this. But before improving it, this is already a good algorithm if rho is not like that. If rho is some large constant, then I would already have a good algorithm here, right? So if you have a problem, and this problem has many solutions in a sense, It can be a SAT instance or any other problem in NP, but if it has many solutions, if the ratio of the solutions, the ratio of the size of G to the size of H is big enough, then you can just apply this Monte Carlo sample. Now, let's think a little bit more about that. So, what ratios can I handle? So I saw that if my ratio is 1/2 to the power of n, then my number of samples would become exponential, and that's too bad, right? Of course, if my ratio is a constant, if my ratio is, for example, I don't know, 1/100, then this number here would be something that is just a polynomial in 1/epsilon and log of 1/delta, and then it gets multiplied by 100, that's fine. It's still polynomial, right? But I can do better than this. I can even handle ratios that are 1 over some polynomial, right? For example, if my ratio is 1/n, then this basically means that here, this row here just tells me that I have to do n times as many samples. If it's 1/n to the power of 5, again, the same thing. My runtime remains polynomial. So my only problem arises when this ratio is really tiny. If this ratio is even bounded by 1 over some polynomial, then still I would be okay. So let's see if we can make this any better. So for the general problem of counting the number of satisfying valuations in SAT, we probably can do better than this anyway. But let's see if there are special cases of SAT that are easier. So when we talk about SAT, we are usually talking about CNF SAT. So in our mind, just imagine how we think about, for example, 3 SAT. It's always that my formula phi is a bunch of clauses, so C1 and C2, so on to C, let's call it M, and each CI is a disjunction of literals. So it's like LI1 or LI2 or so on, or LIK, where each one of these LIs are either one of my variables or the negation of one of my variables. So for example, if I have a 3-set instance, it would be something like x1 or not x2 or x3, and x4 or not x1 or not x2. Okay. So this format, it's called CNF, and CNF stands for conjunctive normal form. But we can also write any formula in DNF, or disjunctive normal form. And the idea in DNF is that the order of these operators basically changes. So every formula I have is now going to be in this format: clause 1 or clause 2 or clause 3 or so on, clause M. And then each clause has a bunch of literals in it, so let's say LI1, but then it has and LI2, and so on, and okay. So for example, in DNF, I can have something like x1 and not x2 and x3, or x1 and x2 and x3 and x4. Now, I expect that, again, you've seen in logic courses that we can write everything, every formula in both CNF and DNF, right? So here, let's say that instead of wanting to count the number of satisfying valuations of a SAT instance, I have a DNF SAT instance. and I want to count this number. Okay, so this is usually just called DNF counting. Now, does this really make the problem easier? Because I just told you that any formula can be written in DNF, right? But to see that it really matters, let's think about the decision variant for a second. So if I give you a formula in CNF, it's NP hard to decide whether this formula is satisfiable or not. It's NP hard to decide if even one valuation exists or not, right? And I mean, it's NP hard even for the case of 3-SAT, where each one of my clauses has only 3 literals. Okay? But if I give you a formula in DNF, and I ask you, does this formula have a satisfying assignment? That's kind of trivial, right? Because in order to satisfy this formula, it's enough to satisfy only one of its clauses, right? So I just go over each clause separately, and I see if I can satisfy that one clause. And satisfying a clause is also trivial. So if I have a clause like this, well, I have to put x1 to be true, x2 to be false, and x3 to be true. That's the only way I can satisfy this clause. Okay? And yeah, if I can satisfy this, then I can satisfy everything. So when I have a DNF formula, either all of my clauses are unsatisfiable, or if even one of them is satisfiable, then the whole formula is satisfiable. So the decision problem for SAT in DNF is actually polynomial time, and it's super easy. So what does this show us? It shows us that the conversion from CNF to DNF has to be hard. And that's actually the case. So all the algorithms that we have for converting a formula from CNF to DNF actually increase the size of the formula and explode it exponentially. So having an algorithm for DNF would not necessarily give you an algorithm for CNF. I mean, it gives you an algorithm, but the runtime might become exponential. Okay, but again, we're not working on the decision problem here. We're just working on the counting problem. So I've given you a DNF instance that looks like this, and I'm asking you how many satisfying valuations does this instance have? Now again, it might be that this ratio rho is small even for a DNF formula. I don't have any reason to say that if a formula is given in DNF, then this rho is large. So it might be that if I just run this simple algorithm, it fails. But now I want to kind of define my sets differently. So I want to give a different definition of the sets H and G, so that this ratio, which was the ratio of the size of G to the size of H, is guaranteed to be small. Okay? And again, by small, I mean that I want it to be 1 over some polynomial. Because as long as I have that, I have a polynomial runtime. Okay. So, not this anymore. Okay. So as we saw before, it doesn't work if I say H is the set of all valuations. If I take all the 2 to the power of n valuations and say that H is all of them, this algorithm would not run in polynomial time. How can I limit the number of valuations that I look into? So again, my formula looks like this. I don't want to have to look into all the valuations. I want to look into only a small number of valuations. So consider this simple case where we have two different clauses. If a valuation satisfies my formula, then it has to satisfy one of these two clauses, right? So I can just take the set of all the valuations that satisfy at least one of these two clauses, right? So I get all the valuations that satisfy this one and all the valuations that satisfy this one. And these will be exactly the set of valuations that satisfy the whole formula. But my problem is that it's not just about creating these sets, it's also about sampling from them, right? So, for example, here if I have, let's say, 10 variables, how many valuations do I have that satisfy this clause? Well, to satisfy this clause, I have to set x1 to true, x2 to false, and x3 to true. But for all the 7 other variables, I can do whatever I want. So I have 2 to the power of 7 different ways, let's say. And similarly here, I have 2 to the power of 6 different ways. But some of these will actually be shared by both of them. So I cannot just say, oh, I take one of these clauses uniformly at random, and then I take one of the valuations that satisfy that clause uniformly at random, right? Because that would not give me a uniform sampling of all the valuations that I want. Okay? So I have to be a little bit more careful. Now, here's the thing. I can say that, consider a formula. Let's say my formula phi is C1 or C2, so on, or Cn. And let's say that I also give you a valuation that satisfies this formula. So let's say I give you some valuation V, and V satisfies phi. What does that mean? It means that V satisfies at least one of these clauses. I'm going to just take the first clause that is satisfied by V, and I'm going to call that the index of V. Okay, so index of V is just the smallest I. So it's I, where I is between 1 and m, and it's the smallest I where V satisfies Ci. So V satisfies Ci, and for every j that is greater than I, for every j that is smaller than I, V does not satisfy Cj. Okay? Again, forget about the formalism. I'm just taking a value for all, a valuation for all of my variables that satisfies this formula. I'm saying since it satisfies this formula, it has to satisfy some of the clauses. I just go from left to right, find the first clause that is satisfied by this valuation. And I call that the index of this valuation. Okay. Now I want to create my set H. My problem before was that I have a bunch of valuations that satisfy more than one clause. So here's what I'm going to do. I define my set H to be a set of pairs. I want pairs of valuations and indices. Okay? And the idea is that I take every possible valuation and every possible index such that this valuation satisfies the clause at that index. Now, why am I doing this? Because my problem before was that I could have a valuation that satisfied this clause and another valuation that satisfied this clause, right? That was fine, but if the same valuation satisfied both of them, I would only have one copy of it in H. But now what I'm saying there is that if you have a valuation that satisfies both of these, then put two copies of it into H. Okay? And of course, if it satisfies, let's say, 10 of them, then put 10 copies into H. So now, at least I know how to take a sample from H. Right? So how do I take a sample from H? Well, first of all, in order to take a sample, what is the size of H? So you see, the size of H is just the number of valuations that satisfy C1 plus the number of valuations that satisfy C2, so on. So this is just the sum of I from 1 to m. Let's call it Hi. So let's say Hi is the set of valuations that satisfy Ci. But how many valuations like that do I have? So if I just have a class, how many valuations are there that satisfy this class? Well, here's what I want to ask you. Can the same variable appear twice in the same class? Well, it can, but if it does, we can simplify it, right? So if somewhere in my class I have something like this, if I have x1 somewhere in the class and somewhere later I have not x1, then this clause is not satisfiable. I can just remove this clause from my entire formula. So I do a pre-processing, I get rid of clauses like this. And also, if I have something like x2 somewhere in my clause and somewhere later, again, I have x2. I don't need the second x2. I can simplify the clause. So I can just say that each one of my clauses has a unique set of variables. So each variable appears exactly once, the ones that are actually appearing. So it's not that all the variables have to appear, but if a variable appears in a clause, it appears exactly once. Okay? So let's say that Ki is the number of variables in class I. Okay? Then when I want to find, so for example here K1 is 3. I have 3 variables here. When I want to find a valuation for this class, I know what values I have to give to the variables that appeared. That's uniquely determined by the class. So for example, here x1 has to be true, x2 has to be false. But for the variables that did not appear in this class, I can choose whatever I want. Right? So how many variables do I have that do not appear in this class? Well, n minus ki. So the total number of valuations that I can have is 2 to the power of n minus k. Okay, so this h, this hi, is 2 to the power of n minus k. Okay, again, why am I going through all this trouble? Because I need to take samples uniformly at random from my set H. And the way to do that, the simplest way to do that, is if I just know what the size of H is, and then I just generate a random number between 1 and the size of H. Right? Okay, so now I can compute the size of H in polynomial time, and actually in linear time. Right? So I just find these ki's, I just sum up the sum, and this gives me the size of H. Okay, now that I have the size of H, I can take a random number between 1 and the size of H, and then that gives me a sample in H. And then I translate it back to this format, and then I need to somehow check whether it's in G or not. Okay? But I haven't defined my set G yet. So I've just defined the set H, which was this weird thing here. But what is my set G? You see, I want to keep the ratio of G to H, right? My set H used to be the set of all valuations, but now I redefined H to be this, the set of pairs of valuations and indices. So I have to similarly redefine my set G so that the ratio of G to H remains intact. Okay? Yes, so I can define my set G to just be the set of all V and I, such that V is a valuation that satisfies my formula phi, and I is the index of V. Okay? Now, why am I doing this? Well, what did I want to count? I wanted to count the number of satisfying valuations, right? So I have this set H, and I know its size. Now I want to have another set G inside here, but I want the size of G to actually be the number of satisfying valuations, because the size of G is what I can approximate using this whole algorithm. Now, if I define G like this, then whenever I have a satisfying valuation, I have exactly one element of G that corresponds to it, right? Because if V satisfies the formula phi, then this I has to be the index of V. So basically, there's only one VI in G, and that's like the case where I is the first index that is satisfied. Okay, so yes, I changed the size of my H, but I kept the size of my G the same. Right, so again, size of G is what I want to approximate, and I kept it the same, even though I changed the definition. Okay, now let's try this algorithm again. Okay, I don't care about the number of samples at the moment. The algorithm has two steps. First, I have to choose a random point in H. And I can do that because I know the size of H. After I choose a random point in H, that's like a V and an I. Right? Now I have to check if this particular VI, this pair, is in the set G or not. How can I check that? Well, there are two conditions, and both of them can be checked in polynomial time. First, I have to check that V satisfies phi. Just put the values in, compute, and see if phi is satisfied or not. The second thing is that I have to check that the index of V is I. Again, finding the index of V can be done in linear time, actually. I can just start from the left and find the first class that is satisfied by V. And yeah, that's the way I can check a particular pair to see if it's in G or not. So I can do this whole algorithm. Now, why did I care about this? Why did I do all these weird things? Because my problem before was that this ratio rho, which was the ratio of size of G to size of H, could become terrible. It could be 1 over 2 to the power of n. But now I want to prove that this ratio is small. So basically what I did was that I had a situation like this. I had a situation where my set H was too large and my set G was really small. So when I wanted to approximate the size of G, most of my samples would just go out of G and they wouldn't really give me any information about the actual size of G, right? But now what I've done is that I've redefined H so that H is much smaller. This was the old H, let's say, this is the new H. So now when I take my samples, it's more likely that I actually hit G, and so I get a better approximation. Okay, yeah, the final step is of course to find a bound on rho, and if we can show that rho is at most 1 over some polynomial, then our whole algorithm runs in polynomial time. Okay. So, what is my rho? Rho is the size of G over the size of H. And remember, the size of G was the number of satisfying valuations, and the size of H is something that we have to find. Okay? Here's my claim. I claim that the size of my set H, which was defined like that, is at most m times the number of satisfying valuations. Okay? It's actually quite easy to see this after I say what the claim is. So let's go back here and let's look at our definition of H. So every point in H is a pair of a valuation and an index, right? But this valuation has to satisfy the class Ci, right? But our formula was in DNF. So if this valuation satisfies Ci, it definitely satisfies the whole formula. So in my set H, I don't have anything that does not satisfy my formula. Every valuation that appears somewhere in my set H definitely satisfies the formula phi. So now the question is, how many times can the same valuation appear? Right? But every valuation appears in a pair with some index, and this index can only be between 1 and m. So every valuation can appear at most m times. So the size of H is at most m times the number of satisfying valuations. That's the claim. And so this is just what I put here. Okay, so given that my set H is now at most m times the number of satisfying valuations, this ratio rho is going to be greater than or equal to 1 over. Okay, so I got a ratio that is 1 over some polynomial. And actually, the polynomial is just linear itself. Okay, let's go back to the analysis that we did. So what I had here, which I erased, was that the number of samples that I need to take was this. I needed to have n, the number of samples, to be 3 times the natural log of 2 over delta over epsilon squared times rho. Okay, so this was the number of samples that I had to take, thanks to Wolfram alpha. And now I know that my rho is at least 1 over m. So I can just set my number of samples to be 3 ln of 2 over delta times n divided by epsilon squared. Okay? Now, what was, and again, I can check every sample in linear time. Right? So my total runtime is just this times some linear function, which is the time for checking each one of the samples. Now I needed this to be a polynomial in the size of the input, 1 over epsilon, and the log of 1 over delta, and it is. So this part, this is actually linear in the size of the input. This is 1 over epsilon squared, right? And this is just like a constant times the log of 1 over delta. So I got my randomized polynomial time approximations. Okay, but one last point that I want you to see is that the fact that my instance was in DNF form is super important here. So if my SAT formula was given me in any other form, for example, if it was given to me in CNF form, then none of these things would go through. Actually, I couldn't even define this concept of index anymore. Because in a CNF SAT, the valuation has to satisfy every clause. But what my algorithm really depends on here is that the valuation has to satisfy only one of the clauses.